Hello all, my name is Supun Nakandala. In this talk, I will present to you our system Hummingbird, which is a tensor compiler for unified machine learning prediction serving. This is a joint work with researchers from Microsoft's Gray Systems Lab, UC San Diego, and Seoul National University. Over the past few years, machine learning prediction serving has emerged as an important systems problem. Increasingly, we are talking about systems concerns like having high throughput, low latency, and also various engineering concerns like maintainability. In fact, it is estimated that ML prediction serving is responsible for close to 50% of the total cost of ownership of ML solutions. The systems community have identified these needs and have invested on developing optimized systems for ML prediction serving. However, the focus of almost all these systems have been primarily on deep learning, a class of machine learning models which are primarily based on artificial neural networks. And support for traditional machine learning models, a term used to broadly identify all the other types of machine learning models, have been largely overlooked. However, traditional machine learning is very popular in enterprise applications. In fact, we have applications like predictive maintenance, supply chain optimizations, and customer churn prediction, which are primarily powered by traditional machine learning. According to a recent survey, it is estimated that 50% to 95% of all ML applications in an organization are based on traditional machine learning. So we face this problem where we have lack of optimized systems for traditional ML prediction serving. Systems used for training traditional machine learning models are often not optimized for serving. And also, traditional ML models are expressed using imperative code in an ad hoc fashion and not using a shared logical abstraction. As a result, if you train a traditional machine learning model using one of these training frameworks, and if you want to deploy this model on a different target environment, you face a lot of problems. This often results in highly complex solutions, amplified engineering costs, and also reduced operational performance. In this work, we propose a novel approach where we reuse deep learning prediction serving systems for traditional ML serving. We have developed a system called Hummingbird that can execute traditional ML models on deep learning prediction serving systems. The benefits of this approach include up to 3 orders of speedups for predictive pipelines against the state-of-the-art frameworks, seamless hardware acceleration with up to 3x speedups compared to handcrafted GPU kernels, and all these benefits with significantly reduced engineering efforts and software complexity, and also with increased portability. In the rest of my presentation, I will first give a brief background on traditional machine learning and deep learning and systems for deep learning prediction serving. Next, I will present to you our system Hummingbird and finally present some experimental results using our system. Traditional machine learning models are expressed as predictive pipelines of directed acyclic graphs composed of featurization and model operators. A traditional ML pipeline essentially transforms the input features through a series of featurization operators like value imputation, one-hot encoding, and scaling, and finally feed these transformed input features into a model operator like random forest model. The featurization operators in a traditional ML pipeline can be either stateful or stateless. And operators in traditional ML pipelines are expressed using imperative code. A typical pipeline can contain tens of operators selected from hundreds of potential featurization and model operators. Next, let's look into deep learning and systems for deep learning prediction serving. In deep learning, the primary abstraction is the concept of tensors, which is the generalization of the idea of vectors and matrices into higher dimensions. A deep learning model is expressed as a directed acyclic graph of tensor operators. Each of these operators takes in input tensors and outputs an output tensor and performs tensor transformations like matrix multiplication, addition, and activation functions like rectified linear units. A typical deep learning model can contain hundreds of these operators with often tens of unique operator types. Systems for deep learning prediction serving essentially exploits this shared abstraction of tensor transformation operations in order to support multiple deep learning frameworks on multiple target environments. For example, systems like TVM, TensorRT, and ONNX runtime can first transform the deep learning models in their original training frameworks into this shared abstraction and then compile these models into different hardware targets. The benefits of this approach includes the ability to perform hardware independent and hardware dependent optimizations in a single place, and thereby significantly reducing the engineering efforts required to compile these models and also enabling increased portability. Next, I will present you a system, starting by explaining the main idea of our system. The main idea of our system is to compile traditional ML operators into tensor operators. And we primarily focus on traditional ML pipelines trained on structured data. We make a crucial observation. Once a traditional ML pipeline is trained, each operator inside the traditional ML pipeline can be represented as a transformation function that transforms input features into output features, or a score value in the case of a model operator. This transformation function is often much simpler than the algorithm used during training. And these transformation functions can be broadly divided into two groups: algebraic operations such as linear regression and algorithmic operations such as random forest and one-hot encoding. Compiling algebraic operations into tensor operators is straightforward. However, compiling algorithmic operations into tensor operations is not that straightforward because these operations perform complex data access patterns and control flow patterns. So the problem that we have now is how can we compile algorithmic operators into tensor operators? Our solution to this problem is to introduce redundancies both in the form of computational and storage, and then make the data access patterns and control flow patterns uniform in these operators for all inputs. Depending on the level of redundancy introduced, there can be more than one potential compilation approach. And Hummingbird is capable of picking the compilation approach that works best for a particular target setting. Next, I will explain this approach, taking an example on how we can compile decision tree based models. Let's assume that we want to perform inference on the given input feature vector using the given decision tree model. We first define set of tensors in order to capture the structure of this decision tree model. Tensors A and B collectively captures the structure of all the internal nodes in this decision tree. Each row in tensor A corresponds to a feature value, and each column in tensor A corresponds to an internal node. Ith element of tensor A is set to 1 if internal node j evaluates feature I, and it is set to 0 otherwise. The jth element of tensor B is set to the threshold value corresponding to the internal node j. Tensor C and D collectively captures the structure of all the leaf nodes and also the path leading to the leaf nodes starting from the root node. Each row in tensor C corresponds to an internal node in the decision tree, and each column in tensor C corresponds to a leaf node. Ith element of tensor C is set to -1 if leaf node j is in the right subtree of internal node I. It is set to 1 if leaf node j is in the left subtree of internal node I. And finally, it is set to 0 if otherwise. The jth element of tensor D is set to the count of all the internal nodes that evaluates to true, which are in the path from the leaf node to the root node. After defining these tensors, we can perform inference as follows. We first perform a matrix multiplication between feature vector and the tensor A to produce an intermediate output which has number of elements equal to the number of internal nodes in this decision tree. We then perform an element-wise equality between this intermediate output and tensor B, which will give us an output indicating the evaluation state of all the internal nodes. We then multiply this intermediate output with tensor C in order to produce another intermediate output which has number of elements equal to the number of leaf nodes in the decision tree. Again, we perform an element-wise equality operation between this intermediate output and tensor D, which will finally give us an output indicating which leaf node was selected for the given input feature vector, which can be then used to extract the prediction value from this decision tree model. In the case of decision tree ensembles, we can create these tensors corresponding to each decision tree model and then batch them together and finally perform the batched versions of the corresponding operations in order to perform inference. If decision tree models have different number of internal and leaf nodes, we can essentially pad the corresponding tensors such that all these tensors have the same dimensions. The above approach, which we call GEM or generic matrix multiplication based approach, essentially evaluates all the paths in a decision tree model. In that sense, it is performing a lot of redundant computations. Also, encoding the tree structure using tensors introduces storage redundancy. However, as we have shown in our experimental evaluations, this approach works surprisingly well on modern hardware for many cases. We have also developed two other tree traversal based tree compilation methods that exploit the tree structure. For tall trees, such as the trees produced by light GBM method, we have developed tree traversal method. For bushy trees, such as the trees produced by XGBoost method, we have developed perfect tree traversal method. More details about these methods and a summary of the techniques used to compile 40 plus scikit-learn operations can be found in our paper. Next, I will present to you the high-level system architecture of our system. Hummingbird has three main components: a pipeline parser, an optimizer, and a tensor DAG compiler. Pipeline parser takes in input in the form of trained traditional ML pipelines and converts them into an internal representation object. Currently, it supports ML pipelines in the formats of scikit-learn, XGBoost, LightGBM, OnXML, and also SparkML. The optimizer then performs a set of optimizations which are unique for traditional ML pipelines. These include heuristics-based compilation strategy selection, feature selection pushdown, algebraic rewrites, and also batching of the stacked models. More details about these optimizations can be found in our paper. Finally, the Tensor DAG compiler compiles the optimized intermediate representation object into a Tensor DAG, which is in the format of the underlying deep learning prediction serving system. Currently, we support TVM, ONNX runtime, and PyTorch and TalkScript. Adding support for more traditional ML training frameworks and also more deep learning prediction serving systems is in the pipeline. Before Hummingbird, traditional ML and deep learning were separated into two different silos with respect to ML prediction serving. However, with Hummingbird, we are now able to unify these two different ML paradigms into a single approach with respect to ML prediction serving. Next, I will present you some experimental evaluation results using our system. As the experimental hardware, we used an Azure NC6 V2 machine, which had an Intel Xeon processor with 6 cores, 112 GB of RAM, and an NVIDIA P100 GPU. The operating system was Ubuntu 18.04, and we installed PyTorch version 1.3, TVM.6, CUDA 10, and Rapids 0.9. As the end-to-end experimental workload, we downloaded all the scikit-learn pipelines submitted for the OpenML CC18 benchmark, which has altogether 72 datasets. Out of these pipelines, Hummingbird was able to translate 2,328 pipelines, which gives us a coverage of 88%. We trained these pipelines on 80% of the data and perform inference on the remaining 20%. We use TalkScript as the backend for Hummingbird. Here I present the relative speedup or slowdown of Hummingbird with respect to scikit-learn on the CPU setting. On the CPU setting, Hummingbird was able to speed up close to 60% of the pipelines compared to scikit-learn, with the highest speedup being 1200x. However, in some cases, Hummingbird was slower than scikit-learn, with the worst case being 60x slower. We tried to accelerate the pipeline inference on GPU using Hummingbird and found that Hummingbird can speed up close to 73% of the pipelines, with the highest speedup being 1000x. However, still there were some cases where Hummingbird was slower than scikit-learn, with the worst case slowdown being 130x. We found that one of the main reasons for this slowdown was that some of these input datasets were in sparse format and required sparse operations. However, in Hummingbird, we forced these operations to be dense operations as the sparse operation support in DL prediction serving systems is not that mature. We expect that as the sparse operation support in DL prediction serving systems become mature, we will be able to narrow this gap. Another reason was that most of these datasets were too small, and especially on the GPU environment, data movement overheads were significant compared to the inference runtimes. Next, I will present some experimental results on a tree model's microbenchmark. For this experiment, we used the NVIDIA gradient boosting algorithm benchmark on 4 different datasets: float, year, cover type, and epsilon. These datasets have different number of features and different tasks. We trained 3 different types of models: random forest, XGBoost, and LightGBM. We trained these models on 80% of the dataset and performed inference on the remaining 20%. For the interest of time, I will report only the batch inference results, which we performed using a batch size of 10,000. We evaluate Hummingbird on both CPU and GPU. On the CPU, we use scikit-learn as the baseline and evaluate Hummingbird on both TalkScript and TVM backends. On the GPU environment, we use NVIDIA Rapids library as the baseline, which is a handcrafted GPU-based tree inference library. Similar to CPU, we evaluate Hummingbird on TalkScript and TVM. We found that Hummingbird's runtime depends on the backend DL prediction serving system that it uses. On the CPU environment, Hummingbird on TVM was able to achieve a best speedup of close to 3x. In the worst case, Hummingbird on TVM was close to 20% slower than scikit-learn. On the GPU environment, we found that Hummingbird on TVM is comparable to Rapid's runtime, with the best and worst runtimes being very close. In general, we found that Hummingbird on TVM performs better than Hummingbird on TalkScript for this tree models microbenchmark. The reason for this was that TVM's ability to fuse multiple operators into a single operator and thereby reduce the operator invocation overheads. Experimental results on more datasets and more drill-down experiments can be found in our paper. In summary, I presented to you our system Hummingbird, which is a tensor compiler for unified machine learning prediction serving. Hummingbird is capable of compiling traditional ML pipelines into tensor computations and thereby reuse DL prediction serving systems for traditional ML prediction serving. Hummingbird is open sourced and is a part of PyTorch ecosystem and ONNX converters. We are currently working on adding more support for more traditional ML training frameworks and also more DL prediction serving runtimes. With that, I would like to conclude and take any questions. Thank you.